Welcome to Dreaming Scientist's Sleepy Stories, a place where the mysteries of the universe guide you toward peaceful sleep. Mass feels tangible. You sense it beneath your hands, steadying you against the pull of the world, offering resistance when you push or lift. Yet, beneath that comforting solidity, physics whispers a different story. At its deepest core, mass is not a substance you can touch or isolate. It is energy, shaped, restrained, held in place, a quiet arrangement of the universe itself. Ever since Einstein revealed the connection between energy and mass with E equals mc squared, we have known that energy can transform into matter, and matter back into energy. But that elegant equation leaves a lingering question. Why does some energy gather and settle into forms that endure, while the rest streams endlessly across the cosmos as light? Why can certain arrangements resist motion, persist, and push back, while others vanish into pure travel? Tonight, you follow this subtle trail, tracing the path from quantum fields to the Higgs background, from the hidden energy bound within protons to the emergence of mass itself, a whisper of structure rather than substance. The journey begins with a simple question. Why does mass exist at all, when energy, left alone, flows freely? Observations from modern physics agree. Unconstrained energy does not linger. Light rushes through the vacuum at a constant pace. Massless particles never pause, never define a resting frame, never settle. From early experiments with light to precise measurements by space-based instruments operated by NASA and ESA, energy prefers motion whenever nothing restrains it. And yet, nearly everything you touch behaves differently. Objects remain at rest. They resist nudges and pushes. They persist, localized and enduring, holding their place in space. This contrast is subtle, but profound. It marks one of the deepest tensions in physics. When Einstein formulated E equals mc squared, it was quickly verified through nuclear reactions, stellar fusion, and particle annihilation. Each confirmation reinforced the principle. Mass and energy can transform into one another with perfect balance. Yet, the equation itself does not reveal the origin of mass. It tells us how energy and matter relate, not how energy chooses to settle. Einstein understood this limitation, acknowledging that the mechanism behind the emergence of mass remained beyond the equation's reach. The next step came from a shift in perspective. Instead of treating mass as a material component, physicists began seeing it as relational, a product of interaction rather than substance. Quantum field theory reframed the stage. Fields are primary, particles secondary. Every particle is now understood as a local excitation of a field that permeates all of spacetime. Mass is no longer a property carried inwardly by a particle. It emerges from how a field responds to its environment, to motion, and to interaction. This view resolves a subtle puzzle. If mass were intrinsic, why would some particles remain permanently massless while others gain weight? But if mass is relational, a natural explanation appears. Fields that interact with particular backgrounds acquire a rest frame, while isolated fields remain unbound, free to move at light speed. The Higgs field is one such background, a quiet ocean filling all of spacetime. It is not emitted, nor does it fade with distance. Certain excitations, fermion and boson-like, gain mass by interacting with this omnipresent structure. The effect is subtle, but profound. It changes the relationship between energy and momentum, allowing a particle to settle into a frame at rest. In 2012, the discovery of the Higgs boson at CERN confirmed this deep connection, revealing the mechanism by which energy quietly becomes mass, giving the universe its enduring, tangible forms. The particle discovered at CERN matched every prediction with uncanny precision. Experiments refined the ways the Higgs field connects with known particles. Some, like photons, remain untouched. They glide effortlessly through space, forever massless. Others, such as electrons and quarks, interact gently with this omnipresent field, gaining the quiet ability to come to rest, to persist. And yet, this story only begins to tell the tale. The Higgs mechanism accounts for a fraction of the mass you can feel in ordinary matter. Within a proton, the mass contributed by the up and down quarks is only a few % of its total weight. The rest comes from a deeper, more dynamic source. the energy stored in the strong force that binds quarks together. Protons and neutrons are not simple clusters of massive particles. They are living configurations held by gluon fields, massless carriers of energy that bind quarks tightly within a confined space. That energy cannot escape. It is locked, woven into the structure itself. Decades of experiments, from deep inelastic scattering at SLAC to modern collider studies, have confirmed that gluons carry most of the momentum inside a proton. Lattice QCD simulations, refined over years of computation, reproduce the mass of the proton using only the energy of these fields. Here, mass is revealed not as a property of a particle, but as the measure of energy constrained, inseparable from its configuration. Everywhere we look, the same principle emerges. In neutron stars, matter is compressed to extreme densities where individual nuclei dissolve into collective field states. The resulting increase in mass energy arises not from new particles, but from confinement, interaction, and the pressure of trapped energy. Across the cosmos, in the annihilation of particles or the collapse of radiation under gravity, mass emerges wherever energy is bound, restrained, and structured. Einstein's spacetime responds not to the origin of energy, but to its total content, the full stress energy, including rest mass, motion, pressure, and fields. Black holes, photon shells, or field-dominated systems all obey the same rule. LIGO and Virgo's observations of gravitational waves affirm this. Gravity responds only to the total energy configuration, indifferent to its history. This reveals a profound lesson. Mass is not a substance waiting to be discovered. It is the signature of energy that cannot disperse, energy locked into arrangements that define a stable frame. Even systems of photons can acquire invariant mass when their motion collectively defines a resting frame. In particle colliders, when photons collide to form massive pairs, the mass belongs to the system as a whole, not to the individual particles. The solidity you feel, the resistance to motion, arises from this same principle. Bound field configurations oppose change because altering their motion requires rearranging energy already locked in place. That effort is what we perceive as inertia. Stability, not substance, is what you experience when you lift, push, or hold. The picture is layered. Higgs interactions explain why some particles can come to rest. Strong interactions, through QCD confinement, explain why most visible matter carries weight. Relativistic field theory shows that configurations, not components, define invariant mass. Gravity responds equally to all of it. Energy does not slow down to become matter, it organizes itself, constrained and persistent. Where constraints hold, mass appears. Where they do not, energy flows freely. And there is a subtle, almost poetic implication. If mass emerges from the response of fields to restriction, then inertia, the resistance you feel when you move, also arises from the collective behavior of entire field configurations. It is not a fixed, internal property. It is alive, immediate, and everywhere, a reflection of energy held in harmonious balance. Part 2. Why did the universe awaken from its massless state? There was a time when nothing in the cosmos could rest. Every particle, every ripple of energy, moved as freely as light itself. In the first moments after the Big Bang, the universe contained no mass in the way we feel it today. Space was filled with radiation, flowing unbound, every form of energy racing at the speed of light. Nothing could pause, nothing could anchor itself. This picture comes not from imagination, but from evidence. Measurements of the cosmic microwave background, by missions such as COBE, WMAP, and Planck, reveal that by the time the universe was around 380,000 years old, it had already begun cooling from an unimaginably hot and dense beginning. Particle physics allows us to trace backward, far beyond the reach of telescopes, into a realm of energies that Earth's most powerful accelerators can only hint at. In that primordial state, distinctions between particle types blurred. Forces we now treat separately, like electromagnetism and the weak nuclear force, flowed together as a single, unified interaction. Particles that would one day carry mass were moving as if entirely weightless, indistinguishable from light. The question is not why mass exists now, but why the universe did not remain forever massless. How did a cosmos of pure radiation evolve into one filled with atoms, stars, and galaxies? The answer lies in a subtle transformation deep within the structure of space itself. A shift in the fields that weave through every corner of existence. As the universe expanded, its energy density slowly dropped. The cooling was uneven, but the overall trend was clear, confirmed by both observation and cosmological modeling. When the temperature fell below a critical threshold, around a few hundred billion electron volts, one field in particular began to behave differently. The Higgs field. The Higgs field was never absent. It was present from the very beginning, an invisible sea filling space. At high energies, it rested in a perfectly symmetrical state. In this symmetry, particles that would later acquire mass could not yet come to rest. They moved freely, as radiation does. But as the universe cooled, that symmetry could no longer hold. The lowest energy state of the field shifted. Without fanfare or explosion, the Higgs field settled into a new configuration, with a non-zero value everywhere. Physicists call this electroweak symmetry breaking. It was a quiet, global reorganization of what was already there, reshaping the way particles could exist. Suddenly, certain fields found that they could now rest. Their motion could be transformed away by the choice of a reference frame. Mass had emerged, not as a substance, but as the possibility for energy to persist in place. Photons, which do not couple to the Higgs field, remained untouched, racing along at light speed. The universe had not imposed mass universally. It emerged selectively, wherever fields interacted with the Higgs background. Evidence of this process is found both in the heavens and on Earth. High-energy collisions in particle accelerators recreate fleeting glimpses of the early universe. In these experiments, particles at energies far above their rest mass behave almost as if they are massless again, echoing the behavior of a universe before electroweak symmetry breaking. The discovery of the Higgs boson in 2012 confirmed the presence of this field, while its surprisingly small mass hints at delicate balances within field interactions. This moment, subtle yet profound, changed everything. Once particles acquired mass, they could slow, linger, and clump. Gravity, which responds to energy in all its forms, began to act on matter that could now remain localized. Over time, these tiny pockets of mass would gather, forming the seeds of stars, galaxies, and eventually the world around you. The cosmos, once a sea of pure motion, had learned to anchor itself. Stability had emerged from symmetry, and with it, the possibility for the structures that fill your universe today. Part 3. Why do some particles gain weight while others remain untouched? The universe is filled with a quiet, invisible presence. A field stretches everywhere, threading through space and time, uniform and unbroken. It does not ripple or flow in ways we can perceive. It does not form clouds, or currents, or concentrations. It simply exists, steady and constant, shaping the stage on which all particles move. This is the Higgs field. Yet not everything that crosses this cosmic ocean responds to it in the same way. Some particles glide through it effortlessly, forever unburdened, while others cannot escape its influence at all. This is not a poetic image. It is a measurable reality, confirmed by decades of particle physics experiments, both on Earth and in space. The reason lies in interaction. Fields interact only when they are meant to. Electrons, quarks, and the W and Z bosons couple to the Higgs field. Photons do not. That simple distinction defines why light travels endlessly at a fixed speed, while matter can pause, resist, and accumulate. Imagine the electron. Before the Higgs field settled into its non-zero state, the electron was like a beam of pure energy, unable to rest, unable to anchor itself. Once the field shifted, the electron could interact. Its energy-momentum relationship changed. Suddenly, it could exist in a frame where it remained still, where inertia and weight became possible. Mass was not given. It emerged from a relationship, a conversation between two fields across the expanse of space. Photons, by contrast, remain unanchored. They are excitations of the electromagnetic field, which does not couple to the Higgs background. Their motion cannot be transformed away. They always move, always flow, and in doing so, remind us that mass is not a universal property. It is relational, conditional, and precise. This realization reshapes your understanding of matter. Mass is not a thing that particles carry like a token. It appears only when energy is constrained by interaction, when fields respond to one another. Without the Higgs field, electrons would race like photons, quarks would wander freely, and the universe would be a vast, restless sea of radiation. The same principle underlies why protons, neutrons, and the vast majority of ordinary matter gain most of their mass through a different mechanism: confined energy within the strong force. But the Higgs field sets the stage. Without it, particles would have no resting place at all. The universe could never form localized structures, never gather into atoms, stars, or planets. Every experiment, from the first collider tests to the precision measurements at CERN that revealed the Higgs boson, reinforces this picture. It is a world where mass is not handed down as a gift, but arises naturally wherever fields couple and constrain one another. A particle at rest is evidence of an invisible order, a subtle architecture woven into the very fabric of spacetime. And so, as you drift through this reflection, you may imagine a universe once unanchored, where everything raced freely. Then the Higgs field shifted, particles learned to rest, and mass emerged as a consequence of connection and interaction. Stability became possible, structure became possible, and the cosmos began to take the forms you know today. Mass is not substance. It is endurance. It is the quiet result of energy held in place, of fields responding, and of the universe shaping itself into something that can pause, gather, and persist. And within that persistence, the world we experience slowly, inevitably, quietly comes to life. Part 4. Where does ordinary matter get its weight? The universe is subtle in how it endows particles with mass. The Higgs field, as we've seen, sets the stage. It allows some particles to exist at rest, to have inertia, to carry a form of weight. But the mass you feel when lifting a cup, the heaviness of a stone in your hand, arises almost entirely from something else. It may seem surprising at first. If the Higgs field gives mass to electrons and quarks, then surely the mass of everyday objects should follow naturally. But protons and neutrons tell a different story. A single proton carries nearly 1 billion electron volts of energy. Yet the Higgs field contributes only a small fraction of that. More than 90% of a proton's mass emerges elsewhere. Neutrons show the same pattern. The matter that builds stars, planets, and your own body is heavy not because of the Higgs mechanism, but because of energy trapped in dynamic, restless fields. This realization was far from obvious. In the 1960s, experiments at the Stanford Linear Accelerator Center sought to probe the heart of the proton. Physicists expected to see something simple: small, solid constituents holding most of the mass. What they found instead was a delicate dance of energy. Quarks seemed almost free when struck at high energies, yet they could never escape the proton. The proton was not a static object. It was a confined storm of fields, each carrying energy, momentum, and constraint. These discoveries led to the development of quantum chromodynamics, the theory of the strong force. Within this framework, quarks are bound together by gluon fields, massless carriers that nevertheless carry immense energy. That energy cannot escape, cannot radiate away. It is locked within the proton, giving rise to the mass we measure. Mass, here, is not a property of the quarks themselves. It is a reflection of how energy is trapped, organized, and confined. As you imagine this, picture a storm contained within a shell, the wind swirling endlessly yet never leaving its boundary. The energy moves, shifts, and interacts, but it cannot escape. That trapped motion is what gives the proton its weight. The heaviness you feel in your hands is the echo of that hidden, ceaseless activity inside every atom. The Higgs field made it possible for quarks to have rest mass, allowing them to form stable structures. But it is confinement, the intricate choreography of strong force fields, that generates the majority of ordinary matter's mass. This distinction is subtle yet profound. It reveals that mass is not simply handed down. It emerges from structure, from relationships, from energy woven into configurations that cannot be undone. Even now, as we lift objects, handle the world around us, or gaze at stars, the story of mass is the story of constrained energy. Fields and interactions, not substance, give matter its endurance, its resistance, its solidity. What seems permanent is, in fact, the quiet consequence of ceaseless, hidden motion. And so, the universe reveals its secret. The weight of the world is not a gift of particles, but the product of energy trapped in elegant, invisible patterns. Patterns that endure, resist, and shape the cosmos. Part 5. The weight of energy. Imagine the forces that bind the universe as gentle currents you cannot see, yet feel in every atom around you. Within the heart of a proton, quarks carry a property called color charge, moving with a restless energy, weaving invisible threads through space. Gluons, massless yet potent, mediate these interactions, linking quarks in an unbreakable dance. Unlike light, which spreads freely, the strong force grows more insistent the farther it is stretched. Try to pull a quark apart, and the energy between them intensifies, until creating new pairs becomes easier than isolation. Free quarks, then, never appear. They are bound, confined, eternal within their tiny domain. This confinement shapes mass in a profound way. Inside the proton, quarks rush near the speed of light, while gluons emerge, interact, and dissolve continuously. The proton's mass does not come from the quarks alone. Instead, it is the trapped energy of this dynamic system that defines weight. Relativity tells us that energy, when it cannot escape, contributes to invariant mass. The proton is a perfect embodiment of this principle. Experimental evidence unfolded gradually, like a soft revelation. Deep, inelastic scattering experiments revealed that gluons carry most of the proton's momentum. Later, high-energy colliders refined these measurements, confirming that gluons dominate internal dynamics even at moderate energies. Simulations using lattice quantum chromodynamics, a computational method that places fields on a discrete spacetime grid, reproduced the proton's mass using field energy alone, without relying on heavy quark masses. This success marked a quiet revolution. Mass, it seems, can arise from energy organized into bound configurations, not from the weight of individual constituents. The proton's heft is not stored in its parts like water in a jar. It emerges from the total energy of a constrained system. NASA and ESA educational materials reflect this understanding carefully. Ordinary matter is heavy not because of the Higgs field, but because the strong force binds energy into persistent forms. The Higgs allows quarks to have rest mass, yes, but the strong interaction shapes the bulk of the weight we experience. Consider a thought experiment. Imagine a universe where quarks have small rest masses thanks to the Higgs, but the strong force does not confine them. Quarks would drift freely, unbound, and protons would never form. Ordinary matter would be feeble, chemistry impossible, stars unformed. Now, imagine the opposite. Quarks massless, but confinement intact. Energy trapped in gluon fields would still create protons of nearly the same mass as in our universe. The dominant contribution to weight lies not in the mass of quarks, but in the energy of confinement itself. In neutron stars, where matter is compressed to unimaginable densities, this principle becomes even clearer. Pressure and interaction energy contribute directly to the star's mass energy content. Observations from NASA's NEASR mission confirm that the strong force remains the primary architect of mass, even under extreme conditions. The early universe tells the same story. Before protons formed, as quarks cooled and bound into hadrons, mass energy appeared rapidly, not because new particles were created, but because energy reorganized itself into confined structures. The cosmos did not grow heavier by adding ingredients. It grew heavier by folding energy into patterns that could endure. This understanding emerged slowly. Quantum chromodynamics resisted easy solutions. Analytic approaches faltered. Decades of computation, experimentation, and patience were needed to confirm that field energy alone can account for the proton's mass. In the words of Frank Wilczek, most of the mass of ordinary matter comes from the energy of gluons. This simple statement captures a deep truth. Weight is not a property handed down from a particle, but a signature of energy trapped in complex, unyielding configurations. As you hold an object in your hand, consider this: the resistance you feel is not from quarks themselves. It is the inertia of confined energy, the ceaseless motion of gluon fields, and the delicate dance that holds the proton together. Every touch is a whisper of fields, a trace of invisible currents that define what it means to weigh something, to matter, to exist in a universe where energy, once constrained, becomes the enduring presence we call mass. Feel the object in your hand. Its resistance is real, tangible, and unchanging, no matter how it came to be. This resistance is not a story of past events. It is woven into the structure of the object itself. In the language of relativity, mass measures energy that cannot escape, energy that remains fixed regardless of how you move. Within a proton, the seething quarks and gluons are trapped, confined in a ceaseless dance, and that energy cannot simply vanish. As long as the confinement holds, the mass endures. Yet, the story of mass is not complete with confinement alone. The detailed behavior of strongly interacting matter, from quark-gluon plasma to the dense heart of neutron stars, continues to challenge and refine our understanding. Experiments in particle accelerators, heavy ion collisions, and astrophysical observations all confirm the same truth. The mass of ordinary matter is not a mere sum of fundamental parts. It is an emergent property, arising from energy trapped, constrained, and interwoven in complex field configurations. Now, notice something subtle. The resistance you feel when you try to accelerate an object, what we call inertia, cannot be explained by Higgs-generated mass alone. The Higgs field tells us which particles can exist at rest. It does not explain why matter pushes back when you try to move it. That push, that resistance, emerges only when motion forces an entire system of fields to respond. After the Higgs boson's discovery in 2012, it would have been tempting to declare the mystery of mass solved. Yet careful summaries from NASA and CERN emphasized a key point. The Higgs mechanism explains rest mass, but it does not fully account for inertia. Rest mass is the ability of a particle to exist in stillness. Inertial mass is the resistance felt when a force is applied. In everyday life, these two seem inseparable, because objects that can rest also resist motion. But in the deeper laws of physics, the connection is subtle and profound. Acceleration is not just a shift of position, it is a gentle, pervasive reshaping of every field inside an object. In a proton, quarks zip at near-light speeds, while gluon fields stretch and pull in constant tension. In an atom, electromagnetic fields weave electrons to nuclei. In a solid, billions of particles interact, their collective excitations shifting together. When you push, every field reorganizes, and that effort, felt instantly across the system, appears as inertia. The response is immediate, not through magic, but because interactions propagate across the object faster than your hand can move. The Higgs field plays its part silently in the background, allowing rest to exist, but it does not contribute to this dynamic response. It does not supply the energy trapped in gluon fields or govern the rearrangement of electromagnetic bonds during motion. When your hand moves an object, you are pushing against the sum of constrained energy, the intricate choreography of fields resisting reshaping, not the Higgs field itself. In this way, the universe whispers a quiet truth. Mass is not just a label for weight or a property of particles. It is a story of energy, fields, and interactions, and inertia is the echo of that story in motion. The resistance you feel, the subtle pushback of matter, is a testament to the hidden currents that hold the cosmos together, a signature of structure and order that began billions of years ago and continues to shape every object you touch. Feel the gentle push as your hand moves an object. That resistance you notice is not imagined, it is real, measurable, and reproducible. You are pressing against the intricate choreography of interacting fields, the invisible web of energy confined and bound within every particle. As quantum chromodynamics revealed, most of the mass of ordinary matter arises not from the Higgs alone, but from energy trapped inside protons and neutrons. And when you try to move that energy, it resists. The stronger the confinement, the more it pushes back. Inertia, in this sense, is the cost of rearranging bound energy as motion changes. Experiments confirm this subtle truth. When particles are accelerated to extreme energies, their response depends not just on rest mass generated by the Higgs field, but on the total energy contained in the system. Two particles with identical rest mass but different internal energy distributions will react differently when a force is applied. At the highest energies, these differences fade, as internal structure becomes less relevant. In special relativity, the story becomes even more precise. Resistance to acceleration increases with energy, not because mass grows in a material sense, but because the energy content itself resists change. NASA's materials on relativity highlight this. Mass and energy are inseparable in dynamical contexts. Even heating an object slightly increases its inertial mass, a fact confirmed in delicate experiments. Inertia emerges only when fields are forced out of equilibrium. At rest, the system is still. Under uniform motion, it shows no resistance. Only when acceleration disturbs the fields does the invisible push appear. The Higgs field alone cannot explain this. It permits rest, but it does not dictate how fields rearrange when motion changes. That response belongs to the energy bound within the system, not the background field that allows it to exist. Historically, physicists wrestled with these questions. Early 20th century experiments tested whether inertial mass and gravitational mass were truly equivalent. Space-based tests, refined over decades, confirmed the equivalence with extraordinary precision. General relativity incorporated this insight, linking gravity to the total energy momentum of a system, not to mass alone. Yet even in relativity, inertia remains a dynamic response. Space-time curvature influences motion, but the resistance you feel arises locally, from the energy woven into fields. Gravity does not create inertia. It mirrors it. This layered picture clarifies the universe's quiet logic. Higgs coupling allows particles to rest. Quantum chromodynamics explains why protons are heavy. Field dynamics reveal why objects resist acceleration. Each operates on its own level, and none replaces the others. While the field-based understanding of inertia is consistent with experiment, it is still incomplete. Researchers explore how vacuum fields interact with accelerating systems, or how inertia emerges in relativistic many-body systems. Yet one truth is clear: rest mass and inertial mass, though numerically equal in ordinary conditions, arise from separate processes. Treating them as identical masks the profound richness beneath. Carl Sagan often reminded us that familiar experiences gain new depth under careful scrutiny. When you push an object, the sensation is not the Higgs field pushing back. It is the collective response of energy arranged in stable configurations, resisting reshaping. The resistance spreads outward, extending beyond the object into the surrounding fields, emerging only as motion forces change. Inertia is not passive. It is alive, a subtle dialogue between energy, structure, and the surrounding cosmos. Acceleration becomes a story told by the fields themselves. They do not yield freely, but respond, redistribute, and maintain harmony. In atoms and solids, countless coupled fields, electromagnetic, strong interaction, and others, create configurations that persist over time. When you apply a force, the system is nudged from equilibrium. The resistance you feel is the energetic echo of that disturbance, the quiet cost of reshaping a bound, structured universe. Even when you strip away every particle, every atom, and every trace of matter, space refuses to be empty. Something remains, persistent and measurable. This is not a metaphor, and it is not speculation. It is a consequence of the deepest laws of physics. For centuries, classical physics imagined the vacuum as a perfect void. Remove all matter, and nothing should remain. But precision experiments proved that this comfort was an illusion. Quantum field theory paints a different picture. Every fundamental field exists everywhere in space, not just where particles are present, but even where no excitation can be seen. A particle is merely a ripple, a disturbance in its underlying field. Remove the ripple, and the field persists in its lowest energy state, the vacuum. Yet even this ground state is not featureless. The uncertainty principle forbids any field from being perfectly still. Fluctuations remain, tiny variations in field values that cannot be switched off. These fluctuations are subtle but observable. In spontaneous emission, for example, an excited atom releases a photon even in complete darkness. Classical physics had no explanation for this. If the vacuum were truly empty, nothing should happen. Quantum theory resolves the mystery. The electromagnetic field, even in its lowest state, continues to whisper, nudging the atom and allowing emission. This restless vacuum shapes inertia itself. When you accelerate an object, it does not resist in isolation. It interacts with the web of fields around it, the vacuum subtly responding, the bound energy inside matter rearranging itself in dialogue with the emptiness that is not empty. Inertia is not a property hidden inside particles, it is a dynamic response, arising from energy distributed across interacting fields and the vacuum itself. Heating an object, accelerating a proton, or nudging a spacecraft, all reveal the same truth. Resistance is universal, immediate, and proportional to total energy content. The Higgs field permits rest, quantum chromodynamics builds mass from bound energy, and the vacuum ensures that acceleration always meets response. In this quiet interplay, you sense a profound lesson. Empty space is never truly empty. It is alive with structure, with potential, with energy locked in patterns too subtle to touch but too real to ignore. Inertia, mass, and motion all emerge from this invisible architecture, a hidden symphony of fields that governs the dance of the cosmos. The vacuum does more than allow processes to happen. It participates in them. A striking demonstration came in 1948, when Hendrik Casimir predicted that two uncharged, parallel metal plates placed extremely close together in empty space would attract one another. This attraction was not due to conventional electromagnetism or hidden charges. It arose purely from the structure of the vacuum itself. Between the plates, certain quantum fluctuations were suppressed, while outside they persisted, creating a subtle but measurable pressure difference. Decades later, experiments confirmed Casimir's prediction with growing precision. Modern measurements at nanometer scales perfectly match quantum calculations. No particles are exchanged. No invisible forces interfere. The effect emerges from the vacuum itself, a realm that refuses to be empty. This revelation reshaped how physicists view motion and acceleration. Space is filled with fields even in their quietest states. Accelerating matter cannot escape interacting with them. Motion is not simply a change in trajectory. It is a dialogue with a pervasive, structured background. NASA and ESA research programs repeatedly confront this reality. Atomic clocks, detector noise, and precision experiments all must account for vacuum fluctuations. Even astrophysical phenomena, Hawking radiation near black holes, the formation of early cosmic structures, cannot be explained without acknowledging the vacuum's dynamic role. On the largest scales, empty space carries energy, contributing to the universe's expansion as what is commonly called dark energy. Acceleration interacts with this field-filled vacuum. Yet the vacuum does not act like a fluid or drag force. Uniform motion passes unnoticed. Only when motion changes, when acceleration is imposed, does the vacuum respond, shifting the relationship between matter and space. In quantum field theory, this is mathematically precise. An accelerating observer perceives the vacuum differently from one at rest. This is the Unruh effect, a prediction so subtle that it is extraordinarily difficult to observe directly, yet robustly grounded in theory. The vacuum is not an absolute, unchanging backdrop. Its properties depend on how it is probed. While no experiment has yet definitively shown that vacuum fluctuations cause inertia, the evidence makes it impossible to ignore. Resistance to acceleration may arise not only from the rearrangement of internal fields inside matter, but also from interaction with the ever-present quantum vacuum. Inertia becomes relational, emerging from interactions that extend beyond the object itself. Historically, the idea of vacuum energy made physicists uneasy. Early quantum electrodynamics suggested infinite energies in empty space, requiring renormalization techniques to tame the infinities. Yet measurable effects persisted. Spontaneous emission, Casimir forces, and boundary-dependent field phenomena could not be ignored. Empty space was not a passive void, it was part of the system, a participant in reality. Carl Sagan often reminded us that the universe is under no obligation to conform to human intuition. The quantum vacuum exemplifies this. It defies everyday notions of emptiness, yet does so in disciplined, testable ways. Every verified effect, every measured force, emission rate, or fluctuation, reflects the vacuum's active structure. This realization deepens the mystery of inertia. It is not stored inside matter. It is a response that unfolds when energy configurations, both in matter and in empty space, are forced to adjust. The vacuum participates in the cosmic dance, shaping resistance to motion, influencing atomic behavior, and imposing constraints on the laws that govern the universe. Once the vacuum is recognized as active rather than passive, another possibility emerges. If energy, whether in matter or in empty space, contributes to inertia and gravity, then mass itself may appear even where no massive particles exist. Light, energy alone, and structured fields could give rise to effective mass. The boundary between substance and structure begins to blur. The cosmos, it seems, is made not merely of particles, but of relationships, of fields, energy, and a vacuum that refuses to be empty. Part 8. How light can create mass. From the very beginning of modern physics, light has been defined as something that cannot stand still. A photon has no rest frame. No matter how fast you move, you will never catch up to it. This is not an assumption, it is a direct consequence of special relativity, confirmed by every precision test ever performed. And yet, under carefully arranged conditions, light can give rise to mass. Not metaphorical mass, not effective mass, but real invariant mass, the same kind that ordinary matter possesses. This surprising fact forces a profound rethinking of what mass truly measures. A single photon carries energy and momentum, yet it has zero rest mass. That does not mean it is weightless in a gravitational sense. General relativity shows that light curves spacetime and responds to gravity. Rest mass, however, is defined differently. It is the mass measured in a frame where the total momentum of a system is zero. For an individual photon, such a frame does not exist. Its motion cannot be transformed away. The surprise emerges when photons are considered not individually, but as a system. Take two photons of equal energy moving in opposite directions. Each alone has no rest mass, yet together the system does. There exists a frame in which their total momentum cancels, and in that frame, the system is at rest. The energy of this configuration cannot be removed by changing reference frames. According to relativity, that energy corresponds to invariant mass. This is not a theoretical curiosity. It is a routine tool in particle physics. In high-energy experiments, photons collide and produce massive particle pairs. The resulting mass does not come from hidden ingredients. It comes from the energy of photons arranged in a configuration that admits a rest frame. Mass, in this sense, is not defined by composition. It is defined by the structure of energy and momentum. Early discussions of mass often focused on particles as discrete objects. Quantum field theory clarified that particles are excitations, and systems of excitations obey rules irreducible to individual components. Experiments at particle accelerators confirm this. When two photons collide in opposite directions, their invariant mass depends sensitively on their angles and energies. Detectors at CERN and other laboratories, supported by NASA and ESA collaborations, reconstruct the invariant mass from photon energies and directions to infer the mass of parent particles. This perspective demonstrates that mass is a property of configurations, not individual particles. Modern physics avoids the outdated concept of relativistic mass, emphasizing that what increases with energy is not invariant mass but resistance to acceleration. Invariant mass exists only for a system that admits a rest frame, and light can participate in this structure, but never alone. Astrophysical observations reinforce this lesson. In the early universe, before matter dominated, radiation shaped the expansion of spacetime. The cosmic microwave background, measured by missions such as Planck, preserves evidence of this radiation-dominated era. In these contexts, energy density, not particle rest mass, governed gravitational behavior. General relativity treats energy and mass equivalently in the energy-momentum tensor, so dense configurations of radiation curve spacetime just like matter. In principle, sufficiently intense photon systems could collapse into black holes, a direct consequence of Einstein's equations. Even more striking is pair production. When a high-energy photon passes near a nucleus, it can transform into an electron-positron pair. The photon carried no rest mass before the interaction. Afterward, two massive particles exist. Conservation laws are upheld. Energy and momentum are redistributed. The mass emerges because the interaction allows the system to adopt a rest frame. This process has been observed countless times. It is an early confirmation of mass-energy equivalence. But the deeper lesson is often overlooked. The photon does not become mass because it slows down. It becomes mass because the interaction allows its energy to be arranged into a configuration that admits a rest frame. This principle applies broadly. Hadrons acquire mass from confined field energy. Inertia emerges from resistance to rearranging energy. Light contributes to mass without ever possessing it intrinsically. NASA materials on relativity emphasize that mass is a property of systems, not merely particles. Detectors measure invariant mass, reconstructed from energy and momentum. Apparent paradoxes dissolve under this view. Light is massless, yet affected by gravity. Light cannot be at rest, yet systems of photons can have rest mass. These statements do not contradict, they reflect different levels of description. Invariant mass depends on whether internal motion can be transformed away, not on the intrinsic properties of individual constituents. Part 9. Why gravity doesn't care how mass is created. Two photons moving in opposite directions have internal motion, but no net motion. Their energy remains. Their momentum cancels. And mass appears. This simple insight reshapes how physicists interpret the boundary between matter and radiation. The boundary is not sharp. It depends on configuration. Matter can behave like radiation at high energies. Radiation can behave like matter when trapped or arranged symmetrically. In cosmology, this fluidity mattered enormously. During the early universe, radiation energy density determined the expansion rate. As the cosmos expanded and cooled, matter energy density took over. The transition did not involve a change in fundamental ingredients, but a change in how energy was distributed and diluted with expansion. Observations from the James Webb Space Telescope now show that massive structures formed earlier than once thought. Those structures required energy to settle into bound systems. Light alone cannot form such structures unless it is confined. Matter provided the necessary mechanisms, but the underlying principle remains: mass follows configuration. It is important to remain precise about what is established and what is not. Physics does not claim that mass can always be generated from light alone under arbitrary conditions. Momentum conservation, interaction cross-sections, and available energy impose limits. What is established is that no massive constituent is required in principle. Energy arranged appropriately is sufficient. This conclusion does not diminish the role of the Higgs field. The Higgs mechanism explains why certain particles can possess rest mass individually. Photons lack that coupling and remain massless. But the Higgs mechanism does not govern system-level mass that emerges from relativistic structure. As Carl Schon often emphasized, the universe reveals its rules through consistency rather than spectacle. The ability of light to give rise to mass without ever having it is one such rule. It is not dramatic when first stated, it becomes profound only when followed carefully to its implications. Wherever energy is trapped, balanced, or symmetrically arranged, mass appears. Wherever it streams freely, it does not. And if gravity responds equally to all forms of energy, then how mass is assembled no longer matters. Gravity reacts the same way whether mass comes from particles, fields, or confined energy. In that behavior, Gravity appears not as something tied to matter itself, but as a response to energy in every form it can take. Gravity does something unsettlingly simple. It pulls on everything that carries energy without asking where that energy came from. Whether mass arises from the Higgs field, from the tension of gluon fields inside protons, from tightly packed radiation, or even from the structured vacuum itself, gravity responds in exactly the same way. This indifference is not poetic. It is a rigorously tested feature of nature, central to modern gravitational physics. Before the 20th century, gravity was often thought of as a force between masses. Heavier objects pulled more strongly, lighter objects less so. This worked for planets and apples, but quietly assumed that mass was a single, well-defined substance. As physics uncovered multiple ways for mass to arise, that assumption became impossible to maintain. Einstein's general theory of relativity transformed the picture. Gravity is no longer a force acting between objects. It is a manifestation of spacetime curvature. Matter and energy tell spacetime how to curve, and curved spacetime tells matter how to move. Crucially, the source of this curvature is not mass alone. It is the full energy-momentum content of a system. That includes rest mass, kinetic energy, pressure, stress, radiation, and even contributions from quantum fields in their lowest energy states. Gravity responds to all of it. No term in Einstein's equations singles out Higgs-generated mass as special. No preference is given to mass that comes from confined gluons or electromagnetic binding energy. These distinctions do not exist in gravitational response. This universality was tested, not assumed. The equivalence principle, the observation that gravitational and inertial mass are proportional, was confirmed with extraordinary precision. Experiments refined over the 20th century, from torsion balances to space-based tests, showed that objects with very different compositions fall at the same rate. Materials dominated by nuclear binding energy fall just like those dominated by electromagnetic energy. Gravity does not discriminate. General relativity extends this result beyond matter. Light bends in a gravitational field. During the 1919 solar eclipse, starlight passing near the Sun deflected exactly as Einstein predicted. Light has no rest mass, yet it gravitates. This alone shows that gravity cannot be responding to mass in the narrow sense. Modern observations reinforce the same lesson. Gravitational lensing measured by NASA and ESA missions shows entire galaxies bending light, revealing mass distributions that include visible matter, dark matter, and energy stored in fields. The lensing depends only on total energy content. It does not reveal how that energy is packaged. Black holes provide the most extreme confirmation. A black hole does not remember how it formed. Whether from the collapse of a massive star, the merger of neutron stars, or a concentrated photon cloud, its gravitational field is determined solely by a few quantities: mass energy, angular momentum, and electric charge. The origin of that mass energy is erased from the external description. This is not interpretive, it follows directly from exact solutions of Einstein's equations. Part 10. Why might mass be an emergent signature, not a fundamental ingredient? Once a black hole forms, all detailed information about its internal composition becomes inaccessible. Gravity responds only to the total energy trapped behind the event horizon. The possibility of forming black holes from light alone follows directly from this logic. If enough radiation is compressed into a sufficiently small region, space-time curvature becomes strong enough to trap it. No massive particles are required in principle. While such conditions are extreme and rare, the equations allow them. Gravity does not demand mass in the particle sense, it demands energy that cannot escape. Astrophysical observations of the early universe reinforce this energy-based view. During the radiation-dominated era, long before atoms or stars existed, the expansion rate was governed primarily by radiation energy density. The cosmic microwave background, measured with exquisite precision by missions such as Planck, preserves signatures of this phase. Acoustic oscillations imprinted in the CMB reveal a universe where photons played a central gravitational role. As the cosmos expanded and cooled, matter began to dominate the energy budget. Gravity itself did not change its rules, it responded continuously to whatever form of energy was present. This continuity explains why gravity appears so indifferent to microscopic details. In quantum chromodynamics, most of a proton's mass arises from confined field energy rather than the tiny rest masses of quarks. Gravity responds to the proton's total mass energy without regard for how it is internally partitioned. Nuclear reactions offer another confirmation. When nuclei bind and release energy, their gravitational mass changes precisely as expected. The equivalence of mass and energy is not a slogan. It is a quantitatively verified principle. General relativity formalizes this through the energy-momentum tensor, a mathematical object encoding energy density, momentum flow, pressure, and stress. Space-time curvature responds to all of these components. Pressure contributes to gravity. Stress contributes. Radiation contributes. Even vacuum energy, whatever its ultimate nature, enters the equations in the same way. Gravity is remarkably democratic. It couples to everything that exists physically, without regard for charge, color, or flavor. NASA materials on relativity often emphasize this universality, noting that gravity is sensitive to energy in all its forms. This universality explains phenomena that might otherwise seem paradoxical. A box filled with light weighs more than an empty box. The difference is tiny but measurable. Gravity accounts for the trapped radiation just as it would for matter. It also explains why attempts to modify gravity face severe constraints. Any new theory must reproduce the observed equivalence among different energy forms. Deviations would immediately appear in precision tests of free fall, orbital dynamics, or gravitational lensing. So far, none have been observed. The story behind these tests is one of patience and refinement. From early balance experiments to modern satellite missions, sensitivity has gradually improved. The microscope mission, for example, tested the equivalence principle to unprecedented precision and found no violations. Gravity does not care how mass is created, it cares only about energy's presence. Conservation of energy momentum remains paramount. How energy moves and transforms shapes space-time curvature, but its origin, internal structure, or history are irrelevant to gravity's response. This indifference has profound implications. It allows vastly different systems to be treated within a single gravitational framework. A star, a photon cloud, a vacuum-dominated region, or a quantum field configuration. All obey the same equations. This unification stands as one of the great achievements of 20th century physics, and it sets boundaries on deeper theories. Any attempt to unify gravity with quantum mechanics must preserve this universality. A theory that couples gravity preferentially to one form of energy would contradict a century of experimental evidence. Carl Schon often spoke about the power of simple rules applied universally. Gravity's indifference to origin is one such rule, simple in statement, but with consequences that span the cosmos. Yet, open questions remain. The precise nature of vacuum energy, the relationship between quantum fields and spacetime geometry, and the role of gravity at the smallest scales continue to be explored. Observations from JWST and future missions may illuminate how energy behaved in the earliest moments, where gravity and quantum effects were both dominant. What is not in doubt is the principle itself. Gravity measures energy's presence, not its pedigree. It responds to what is there, not how it came to be. If mass can arise from energy configurations, if inertia reflects how fields respond, if the vacuum itself participates, and if gravity responds to all of these without distinction, then mass no longer appears as a fundamental ingredient. It begins to resemble a recurring signature, an emergent property that appears whenever energy becomes constrained in specific ways. Seen from this perspective, mass is not a building block but an indicator of how energy organizes itself within spacetime. Everywhere physics has looked closely enough, mass appears only after something else is already in place. It follows structure. It follows constraint. It follows situations where energy, otherwise free to move, becomes trapped or symmetrically arranged. That pattern is not philosophical, it is empirical, observed across every scale where reliable data exists. At the smallest scales accessible, mass does not behave like a fundamental building block. In the Standard Model, the basic entities are fields. Particles emerge as excitations of those fields, and their ability to possess rest mass depends on interaction. The Higgs field does not inject mass as a substance. It reshapes how certain fields relate energy to motion, allowing a rest frame to exist. Where that interaction is absent, as with photons, mass does not appear. This is not interpretation. It is exactly what collider experiments measure. Yet, even the Higgs mechanism accounts for only a fraction of the mass we encounter in everyday matter. The rest emerges from the intricate dance of fields, energy, and constraints, a signature of energy organized within the fabric of spacetime. Protons and neutrons, which dominate the mass of ordinary matter, derive most of their weight not from the quarks themselves, but from the confined energy of gluon fields. Quantum chromodynamics reveals that these fields, trapped under confinement, store enormous amounts of energy that cannot escape. That energy contributes directly to mass. Remove the confinement, and most of the mass disappears, even though the quarks remain. Again, mass follows structure, not constituents. At larger scales, the same pattern persists. Systems made entirely of massless components can possess mass when energy is arranged in a configuration that admits a rest frame. Two photons moving in opposite directions form a system with invariant mass. Radiation trapped in a cavity adds weight to that cavity. These are not semantic subtleties. They are daily tools in experimental particle physics, where invariant mass reconstruction is among the most reliable methods available. Gravity reinforces this picture with striking consistency. In general relativity, spacetime curvature responds to the full energy-momentum content of a system. It does not respond to mass as an isolated concept. Binding energy gravitates. Radiation gravitates. Vacuum energy, whatever its ultimate origin, gravitates. Black holes formed from collapsing matter are indistinguishable, in principle, from those that could form from intense concentrations of radiation. Gravity measures presence, not pedigree. This universality places strong constraints on how mass can be interpreted. If mass were fundamental, gravity would need to distinguish between energy packaged as mass and energy that is not. No such distinction has ever been observed. Precision tests of the equivalence principle, including space-based experiments, show that objects fall identically regardless of internal composition. The gravitational field responds to total energy with extraordinary fidelity. Inertia completes the pattern. Resistance to acceleration does not behave like a static property stored inside particles. It appears only when motion changes. It scales with total energy. Heating an object increases its inertial mass. Changing internal energy distributions changes resistance. These effects are small but real, and they are consistent with relativistic predictions. Inertia behaves like a reaction of field systems being forced out of equilibrium. The vacuum itself refuses to be excluded from this story. Quantum field theory shows that even in the absence of particles, fields retain fluctuations. These fluctuations produce measurable effects, from spontaneous emission to the Casimir force. Accelerated systems interact with this structured background. While physics does not yet claim that inertia is fully explained by vacuum interactions, it is clear that the vacuum is not passive. Any account of mass that ignores it remains incomplete. Across all these domains, the same theme emerges. Mass is not introduced as a primitive element. It appears when energy is constrained, balanced, confined, or symmetrically arranged. Where energy streams freely, as with an isolated photon, mass does not appear. Where energy is trapped or internally balanced, mass does. This does not make mass illusory. It means mass is descriptive rather than foundational, a way of accounting for how energy behaves when freedom of motion is limited. In this sense, mass resembles other emergent quantities in physics. Temperature is not fundamental. It emerges from collective motion. Pressure is not a substance. It emerges from interactions. Mass, in modern physics, increasingly resembles these quantities rather than an indivisible building block. NASA and ESA descriptions of fundamental physics often emphasize this layered structure. Mass is presented not as a standalone concept, but as something that arises from deeper mechanisms. JWST observations of early galaxies show that massive structures formed rapidly once energy could settle into bound systems. Mass followed structure, it did not precede it. It is important to be precise. Physics does not claim that mass is fully explained in all contexts. The origin of vacuum energy remains unresolved. The nature of dark matter, which gravitates but does not interact electromagnetically, is still unknown. Whether mass emerges from deeper principles at the quantum gravity scale remains an active area of research. What is clear is that treating mass as fundamental has become increasingly unnecessary. Every confirmed mechanism that produces mass does so through interaction and organization. No experiment has required mass as an irreducible substance. This perspective aligns with a broader trajectory in physics. Concepts once considered fundamental often turn out to be effective descriptions. Absolute space gave way to spacetime. Force gave way to interaction. Particles gave way to fields. Mass now appears to follow the same path. Carl Schon often spoke about the power of asking where familiar ideas come from rather than assuming they must exist. Mass, so central to everyday experience, turns out to be remarkably subtle when examined closely. It is not the starting point of physical explanation. It is a recurring signature, appearing whenever energy loses the freedom to move without resistance. Seen this way, mass becomes a record rather than a cause. It records how energy is arranged within spacetime, how fields interact, how configurations stabilize, and how motion becomes constrained. Wherever those conditions are met, mass appears. Wherever they are not, it vanishes. This does not diminish its reality, it deepens it. It places mass within a network of relationships that spans from quantum fields to cosmic structures. It allows the same concept to apply consistently to protons, photons, stars, and black holes without contradiction. As observations grow more precise and theories more unified, this view will continue to be tested. Future experiments may reveal deeper layers beneath the mechanisms we now understand, perhaps showing that even fields and spacetime themselves are emergent. Still, if that happens, mass will likely follow the same pattern, appearing not as a primitive ingredient but as a reliable signal of constraint and structure. For now, physics offers a coherent vision. Mass is not frozen energy. It is energy that cannot move freely. It is energy held in place by interaction, symmetry, and structure. It is a footprint left wherever motion meets resistance. As this long chain of ideas settles, there is no need to hold on tightly. The universe continues its work whether we watch or not. Fields interact, energy organizes, structure persists, and mass appears exactly where it must. Thank you for spending this time here and following the story all the way through. As the night settles and everything slows down, may the thoughts from this journey rest gently in the background. Wishing you a peaceful, comfortable sleep and a gentle start to the next day.